Is that? Okay, well here we are at day 10. I said yesterday that I would get to a problem and ran out of time and didn't get to it, so we'll get to that right away today. Let me have us to take a look at a couple of predecessors of that problem first. These are examples that I was going to have us look at, but we ran out of time. So let's look at them, and then I've also got the example that we tabled yesterday. So let's look at this one. These are kind of carryover problems from finding inverses and the inverse of an exponential being a logarithmic function. So these should be involving logarithms in some way. So let's say we start with the equation, the function natural log of x equals 2, and we want to solve for x. So you probably don't know the number right off the top of your head that when you take the natural log of it, you get 2. But remember what the base is. Isn't natural log of x the same thing as log to the base e of x, right? Same thing. Now, can that logarithmic statement be written as an exponential statement? And if the answer is yes, then I think we've got a quick and easy solution to this. What's the base? E. What's the logarithm or the exponent? 2. And what should we get when we raise e to the second? Better get x. There's our solution, right? So simply by either rethinking or rewriting the original problem so that it actually shows the exponent, shows the base, log to the base e of x, then rewriting it in exponential form, there's what x needs to be. Now see if that makes sense. This can be one of those self-answering questions again, if you ask it properly. When you're trying to find the natural log of something, what's the question that you ask yourself?
What they're raised to.
Okay, to what power do you raise e, right?
Mm-hmm.
Trying to find the logarithm, in this case find the natural logarithm. What power do you raise e to get what?
X.
E squared? Doesn't that kind of answer itself? What power do you raise e to get e squared? Well, I think it kind of answers itself. 2, right? As I said yesterday, what's the name of your brother whose name is Bob? For goodness sakes, it's Bob. So what power do you raise e squared? What power do you raise e to get e squared? The only way that works is if that question mark is 2. Everybody all right with that one?
Mm-hmm.
Okay, the next example that we need to be prepared to handle. What power do we raise to? There I'm asking myself that question again. Log to the base 2 of 11 is something. So what power do we raise to? Well, I don't know that one either. Any recommendations here? And this is kind of a general recommendation. When the thing you're solving for, am I off the screen here? I guess I'm okay. The thing you're solving for is in the exponent position. You've done this before. How do you get it out of that position? Take the log of both sides. Now, does it matter? With a base 2 problem, can we take the natural log of both sides or the log of both sides?
Couldn't you do the change of base there?
Yeah, there is a, in your text, there is a kind of a way, kind of a change of base conversion. Mm-hmm. And you can learn that and memorize that. But that process only works for this kind of problem. Mm-hmm. Whereas in general, when you have a variable in the exponent position, I'd rather you know what to do that works all the time. So if you find that in your book, I'm not going to say it's not there. I mean, it's there. But I think better yet, how do we solve any kind of a problem where the variable's in the exponent position? So we could take the natural log of both sides. That converts it to a base e problem. Or we could take the log of both sides. That converts it to a, just see log. What is that? What base is that? That's base 10. So if you're going to use your calculator especially, you'll want to convert it to a base e problem, natural log, or a base 10 problem, common log. So let's in fact show that both give the same answer. So if we take the natural log of both sides, we get that. Now why does that help the cause?
Because then you can break down 11. Like 10 to the first plus 10 to the 0.
I think we want to look at the other side.
Oh.
Can take
Yes, sir.
Because you can raise 2 to the x to the e. You can have e to that, and they'll bring the exponent down.
Okay.
And
So
it
the
cancels out the natural.
end result is we've got a property that says when you're trying to find the log of something that is raised to a power, can't we bring that power out in front? Which is the end result of what you just said. Everybody all right with that? Because what's a logarithm? A logarithm is an exponent. When you have you're trying to find the exponent of something that is itself raised to a power, you've basically got a power to a power. So we can multiply the exponents. We want to isolate x. Somebody's got a calculator fired up and ready. What is the natural log of 11 divided by the natural log of 2?
3.46.
Okay. Can you give me another decimal place?
Oh, okay. 3.459.
Now, is that a believable answer? Well, let's go back to the, maybe not the original problem, but at least to our rewritten version of the original problem. We're going to raise 2 to the 3.459. Does that seem reasonable that that would be 11? Well, 2 to the 3 is what? 8.
8.
And 2 to the 4 is 16. Reasonable? Seems kind of reasonable. Now, is this a problem that you could punch into your calculator pretty quickly to get a quick check on that? I think you could, right? Even if you have like just a scientific calculator, which by the way, that's all I have, you can punch, you have a x to the y key or an a to the b key, you can punch in these two numbers right here, and you should get something very, very close to 11. We're not probably going to get exactly 11 because this is an approximation. Now, you mentioned earlier the change of base. This is what's in your book in that particular area for that change of base theorem. If you want to use that, that's fine. But I would rather you learn a process that's going to work for all problems of this type. Now, could we do this using logs? The log of both sides, now we're converting it to a base 10 problem. Again, that's what we wanted to happen. So x times log of 2 equals log of 11. Divide both sides by log of 2. And the reason is that we've got a choice. We've got a base 10 or base e. We ought to take either one of those if we're going to use our machine to help us solve the problem. Somebody take your calculator and take the log, base 10 logarithm of 11 and divide it by the log of 2. And I am hoping that you get 3.459 or something real close to it. Did I do that? Get that? So it doesn't matter if you change it to a natural log problem or a common log problem, as long as you're consistent from that point to your solution. So the answer for x is that. Questions on that? Okay, now, this is what I said we would get to yesterday. So this was, the question was asked right at the beginning of class about this problem. I think it's from section 1.5. Is that correct? Anyway, page 64, problem 23. And we had to develop our own formula. I think there were 100, what were they talking about? Bacteria? Something that was growing, and it was doubling every 3 hours. So we developed this formula, and then part of the question was to use a graph to pick off the T value, how much time would have to elapse in order for this initial set of 100 bacteria to grow into a set of 50,000 bacteria. So let's take what we just reviewed with logarithms and see how we can solve this. To solve for T, how many hours have to go by for the final amount? That's what we want, right? We want to know what is T in order for the number in the sample to be 50,000. So better than a graph that we might, kind of estimate on a picture or a calculator. What's the process? Okay, let's isolate the term that has the variable. I like that. Divide by 100. So we now have 500 equals 2 to the T over 3. Now what? Log or natural log of both sides. And that's the advantage that we pick up here by taking the log of both sides. And that is what on the right side? The T over 3 comes out in front in product form. We want to isolate the term now that has T in it. So it looks like we need to, what? Multiply by 3. And divide by the natural log of 2. Somebody's got your calculator moving and shaking. What is 3 times the natural log of 500? Take that result, divide it by the natural log of 2.
26.897.
And that's hours, right? Wasn't it 3 hours? Now, we're not going to take the time to do this here, but if it doubles every 3 hours, could we go through the process of doubling it and then doubling it again and doubling it again, right?
Mm-hmm.
And get up to the point where, well, if we do that every 3 hours, we could get to what? Couldn't check this exactly, but we could check what? Where it would be at increments of 3 fairly easily.
Mm-hmm.
So you could start the process. Time 0, it's at 100. So at time 3, it's at what?
200.
200. At time 6, it's at 400. At time 9, it's at 800. And you can continue that process and check this and see if it seems reasonable. But I think that process of solving it exactly is going to serve you a lot better than just picturing it and trying to pick a point off of the graph. Questions on that? Okay, and I'm hoping that finishes our review of logarithms. I think that suffices. Any questions? I know we've got a couple questions pending that we'll try to get to, but they're not on logarithms.
There was question 24 part D.
24 is on logarithms
It's,
or from the previous set?
Same.
Previous set? What page?
Same page.
Same page, 64.
64? And what problem, please?
24.
24.
D.
D, same process, right? Use the graph to estimate the time required. So you'd be solving for T for the mass to be reduced to 0.01. Let me set it up, and then you could use the same process. So this is page 64. Number 24. I guess we'll have to build the function. Have we built the function on this one? Not sure that we have. An isotope of sodium, apparently a radioactive one, has a half-life of 15 hours And a sample of this isotope has mass 2 grams. So some later amount is found by taking the initial amount, which is 2, times what's going to happen. It's going to be cut in half every what? 15, right?
Yep, 15 hours.
Same type of function we had in 23. And then the last part of that, which he's asking a question about, we want to know when it's been reduced to 0.01 grams. So we want the f of t to be 0.01. I don't know that you have to do this next step, but I would recommend it. Nah, it's not. I don't know that we're going to gain a whole lot by that, but you could change it to a base 2 problem. How could you change it to a base 2 problem as opposed to a base 1/2? So you could solve this for t, or,
Would you make the exponent negative?
yes, that one. So, and I don't think, because we're just going to punch buttons on a calculator, I don't think it makes that much difference. But either one of those, using logs or natural logs, can solve for t. Now, if you notice in this problem, we start with 2 grams, and then this is a lesser amount, which we would expect it to be. It's a decay problem. And on the prior problem, we started with 100, and we ended up with 50,000, which we would expect to be a greater amount because it was doubling, right? But basically, the method of solution is the same. Does that help on that one?
Mm-hmm.
So then you'd use logs to solve for t. Okay. Would all of you feel comfortable, if you're very life dependent on it, without a calculator, that you could graph that? Not if your life depended on it? Could you graph this? Without a calculator, could you graph y equals e to the x, even if it's a rough sketch? Okay, how could you use this to help you graph this? They're inverses of each other, right? So you can draw in the line y equals x, just kind of take the symmetric image of the points. So if you know that y equals e to the x looks roughly like that, then your knowledge of inverses and properties of inverses ought to get you to this, right? So they are the mirror image of one another on either side of the line, y equals x. Now notice this, and this will come into play in calculus because we analyze kind of how curves progress in the plane. Y equals e to the x is an increasing function, right? We take its inverse. We flip-flop x's and y's. What about its inverse? Isn't it also an increasing function? Mm-hmm. Also increasing. But are they increasing at the same rate? In fact, no, very, very differently. As you move out to the right, don't the tangent lines here get steeper?
Mm-hmm.
And as you move out to the right here, what happens to them? They get flatter, right? So very, very different rates of increase, but they're both increasing. All right, so if this is what natural log of x looks like, now that you've saved your life here and you've graphed it, what would you do to just our friend there, natural log of x, to graph this one?
Shift to the right.
Right 2? This means we're going to take that same graph, lift it up, slide it over 2 units, and flop it right down, right? Yes, sir.
So the graph of the natural log goes through 1, 0 on the
Yes,
1, 0?
yes. So this is the point 0, 1. So its symmetric image is 1, 0. So in that fact, that's a good way to just start taking points and sliding them over, as well as, and let's do a little bit more with this before we leave it. Not only could you take that point 1, 0 and slide it to the right 3, wouldn't it be advantageous to take this line, which in this case is the y-axis, or x equals 0, isn't that asymptotic? Isn't the curve asymptotic to that?
Mm-hmm.
basically slide the asymptote over as well. So we would want to slide the asymptote over 2 units. Which was the y-axis, now is the line x equals 2. And then slide that point 1, 0 to the right 2, which is now what? 3, 0. And we're going to look something like that, right? And lastly, not that we need to picture it, but do you feel confident that you could picture that one? This piece right here means we go to the right 2. What about this piece right here?
Up 5.
Up 5. So translated versions of natural log are just the same as translated versions of parabolas or ellipses, or circles, or in this case, we've got a natural log that needs to be translated. Okay, that should wrap us up from logarithmic functions. I feel like most of that is review. Very, very little of it is new to you, I hope. Now this next section that we'll look at today and finish up tomorrow has to deal with parametric equations. This may not be something that you've looked at in depth. So we'll slow down just a little bit here because I think that most of this is probably new for you.
Where does the test material stop? Is this all going to be on the test?
Yes.
All right.
Yeah, everything that we cover prior to test 1 will be included. And some people have already asked me about that, so while we're talking about that, I'm not going to ask you questions that have you fill in the blank on definitions. It's going to be a problem solving, so if we've done an example in class, or I've asked you to do a problem for homework, that's fair game for the test. And I already told you I think that we're not going to review a whole lot in tomorrow's lesson because it's, for the most part, review already. It seems a little bit redundant. But in general, yeah, it's not. You're not going to have to write an essay on how you feel about hyperbolas or something. Okay, so it's a problem-solving type test. If I give you the equation of a parabola, let's say, could you find the vertex of it and sketch it? Or if I gave you something that needs to be shifted or translated in the plane, can you pick it off of the function and actually slide it to the right 2 and up 5 and sketch it for me? Yes, sir.
Are calculators allowed to be?
Calculators, fine. Graphing calculators are fine, with the exception of a TI-89. Have I not said this already? TI-89, nix on that one, and a TI-92. And the reason why is you can do calculus with those, and I don't want to know if your machine knows how to do calculus. Eventually, I want to know if you know how to do calculus. So you'll have to find and borrow another calculator if you have a TI-89 or a TI-92. Otherwise, you're fine. Okay? Okay, parametric. Equations. So we're going to have not just a function that has x's and y's in it, but we may have x defined or described as a function of t, and y defined or described as, I don't want the same function, some other function of t. So the t here is called the parameter, and the combined equations here are the two parametric equations. So the parameter is t. And t is used a lot of times because you can let it be time, and then as t goes from 0 to 1 to 2 to 3 to 4, you can actually track how the graph itself progresses. So it's not just a set of points, although it is that. It's a progression of a set of points. So we actually have some direction to the set based on how we let t go. So points that we're used to being in the form of x and y are now going to be in the form of some result from the f of a t value and the result from the g of a t value. So have you had any parametric equations at all? In high school math or anything at all? You've had, a couple of you have had some parametric equations?
Sounds familiar.
Okay. Let's take a look at an example. You've got an example in your book that's a very good example, and I trust that you can read and look at that example. I've got another example that I want you to do so you see another one. One of the examples in the book is so good that we can't not do it. We have to do that. It's kind of a classic example. But the first example, I've chosen another one. This is out of the book, but it's out of the problem set. It's page 81, problem number 6. X is some function of t, and y is another function of t. So here's our two parametric equations. Now let's see, as we let t go from, I don't know, let's just arbitrarily, -2, -1. Obviously t's not time here if we're going negative. But -2, -1, 0, 1, and 2. So we'll take t through some paces and then see what the corresponding x's and y's are and plot them. Anybody have an idea what that is? If we were to plot this in the xy Cartesian coordinate plane, what the end result is, kind of hard to tell, isn't it?
Parabola?
Parabola, why might you guess that?
Because it's t squared minus 3t plus 6. I mean,
Okay.
if you combined them.
Okay? We have kind of a linear expression and a quadratic expression, so parabola. Function type parabola or non-function? Non-function?
Yeah.
Okay? Now, part of what I want us to do at the end of this problem is to get rid of t, get rid of the parameter, and have an equation that only has x and y in it. And then I think we ought to be able to identify that. But let's just plot some points here first. So let's plot for certain t values. And I'm just arbitrarily picking some t values. A lot of times you'll actually be given a set of values for t, and those are the only ones you can choose. We weren't given that, so it's wide open. So I'm just starting at -2 and picking integer values and see what we get. When t is -2, what's x? 4. And what's y?
Oh, why?
0.
0.
Hmm?
0.
0? 6 minus 3 times -2.
That's good. 12.
12, there we go.
Okay.
I was hoping it wasn't me. When t is -1. 1. And y is what?
The 9.
9. Almost got you on that one. Okay, when t is 0.
0.
0, and y is
6.
6.
6. There we go. You weren't going to miss that one. T is 1. X is
3.
1.
3,
1,
And y is
3.
3. So it looks like the y's are just dropping 3 each time, right? Kind of makes sense based on the linear relationship there.
4.
And t is 2. X is 4.
0.
And 0.
Mm-hmm.
Okay, so knowing that t has progressed from -2 to +2 on every integer, let's see what the points are. So it looks like we're going to go from 4, 12 is where I start, just in the way I chose the points, to 1, 9, to 0, 6, 1, 3, to 4, 0. Let's see what we get here. 4, 12. And then we're going to head in the direction of 1, 9. Zero 6, 1 3, and 4 0. So it looks like we're going this way.
That is a function. No, it's not.
Now, do you see how it is? Looks like a parabola, right? Part of a parabola. If we graphed more of it, it would be up here, right, and be heading in this direction initially, and then take off in this direction from that point. We didn't graph it all. But notice it's not just a parabola, it's a parabola that has some direction to it, or some kind of built-in motion because of the way t is progressing. If you allow t to progress kind of logically, then we have points in this parabola that progress with the upper piece first down to the vertex and then carry on with the lower piece. Everybody okay with that? Kind of having a little arrow attached to it. Can we combine the two equations into one? So we want to take this and this, get rid of t. Can we do that? How do you want to start that? Can we take this one and solve for t? Right? It is linear, so I think we ought to be able to solve that for t in terms of y. So let's, subtract 6 from both sides? And then divide by -3. So there's what t is equal to from the second equation. Take that and take that result and plug it back into the first equation. X is t squared. So there's our new quantity that represents t. Square it, right? So we've eliminated t. Does that look like a parabola to you? A little more recognizable it is to me that it's a parabola. It's linear in x and quadratic in y. Does that look like a non-function kind of parabola? The function kind of parabola looks like this, right? The non-function looks like this, right? So we've got the y's squared, so that's a non-function type of parabola. So if you want to eliminate the parameter, you can do that, solve one of them for t, and plug it back into the other. Okay, here's the one that's in your book that I know you can read and study, but it's such a classic example that I feel like we have to look at it in class as well. Questions on this one before we leave it? Everybody all right with that? Okay, this is example 2 in your book. Use t or theta t. And this is probably such a classic problem that you'll recognize it if you've done anything with parametric equations, even if you haven't done anything prior to today. Anybody tell me what that is?
Piecewise.
Recognize that at all? Tiffany?
Is it a piecewise function?
What? No. Try to think if that's... No, I don't think it's piecewise function. I mean, we're going to put some pieces together based on points that we plot from t going from 0 to 2 pi. But does everybody recognize this? Finish that for me. 1. What's the cosine of t? It's x, isn't it?
X.
What's the sine of t? Y. Okay, now it may not have looked real familiar in its original form or its parametric form, but if x is the cosine of t and y is the sine of t, what do we get when we eliminate the parameter t? We get a circle, right? A pretty simple circle. Center is at the origin and a radius of 1. So that's what that set of parametric equations is. Now, a circle, center at the origin, and radius of 1, isn't that sometimes called the unit circle? I'm trying to kind of take us collectively to something that I think will ring a bell here. And what do you know about points on the unit circle as they progress around the unit circle?
Okay, from 0 to 2
Cosine.
pi.
Goes
Sine.
to 2 pi.
Okay, there's the 2 pi, all right? There's some, but isn't the x value
Cosine.
the cosine of t? Remember on points on the unit circle? Remember the big old diagram you had in your trig book and you're studying radian measure and cosine, sine, tangent, secant, all that stuff. And here's this unit circle. Your former friend. Now we're getting reacquainted to the unit circle. And the x value was the cosine of t, and the y value is the sine of t. Does that ring a bell at all? And then you could actually plug in different t values, whatever t is. T is the central angle that got you there, and plug it in, and it would generate the point. So here we are, right there. There's the two parametric equations that generate the unit circle. So we've done the second part first here. We've eliminated the parameter just so we could get it into a form where we could recognize what it is. Now we could plot some points. Let's do that. So we have a restriction here, right? T can go from 0 all the way up to 2 pi. That's all we need anyway. If we went more than that, we'd just generate the same set of points. What's the cosine of 0? 1. What's the sine of 0? 0. Notice a little hesitance there to give me answers. Let's see what happens as we go around here. Maybe that's too much, but I think we already know it's a circle, so let's just kind of roll on over to pi over 2. What's the cosine of pi over 2?
0.
0. And the sine of pi over 2? 1. Pi, cosine of pi,
Negative
Negative
1.
negative 1. Sine of pi,
0.
3 pi over 2, cosine of 3 pi over 2?
0.
0. What do we got here? Negative 1?
1.
And now we're back to 2 pi. We should be right back where we started, right? Cosine of 2 pi, it's periodic, and its period is 2 pi, so we ought to be the same place that we started. So if you plot those points, in fact, let me just point them out. Here's our starting point, right? 1, 0. So we start to track this thing in this direction, and then we go to 0, 1, and we continue to negative 1, 0, which is right there, 0, negative 1. And then back to our starting point of. So it's a circle, but it's a circle really with a little added twist there, is we do know the direction of how the set of points are plotted. Questions on that, anybody? It's in your book, but that's just such a classic example. We have to look at that one. Everybody all right with that? Okay. There is an example of this type in your book, but again, I chose another one, so you can look at the one in your book and then also look at this one. This is from page 81, which is the problem set, and this is number 13. Similar to the example that's in your book, but it's a little different function. And it's kind of related to what we just looked at too, which is another reason why I chose it. Well, we just had an example that was sine by itself and cosine by itself. So if we're trying to eliminate the parameter, since we already know that sine squared theta plus cosine squared theta is 1, what is sine squared theta in this problem? It's x, right? And what's cosine squared? Y. So a little different animal. What do we get? Not a circle with center at the origin, radius of 2. What's x plus y equals 1? That's a line. If we solved it for y, what? Negative 1x plus 1, right? So it's got y-intercept of 1 and slope of negative 1. Do you know that our final answer is not that set? It's part of that set. And let's see why. So here's what we think it is at this point in time. Line with y-intercept 1 and slope of negative 1.
I'm confused on why sine squared theta equals x, or turns into x.
That's x. It's not
Okay.
sine here, it's sine squared. So it's defined differently from this is a new example.
Okay.
And y is defined differently. It's defined as cosine squared. So similar beginning to the problem, but it's different original definition for x and y. Now, go back to what x is. It's the sine of something squared. When you square something, what do you always get? Positive, or at the very least, 0, right? So could x ever be negative?
No.
Okay. X is non-negative. Okay, look at y. Y is the cosine of something squared. Could y ever be negative? Can't square something and get a negative. So if we take our line, we think it's the whole line, but we know from the original parametric equations that x is never negative and y is never negative. So what parts of the line will we never actually come up with?
The one's not in quadrant 1.
Okay, so the only actual solution points are these. So we can throw that set out and throw that set out, right? So we get a part of a line, but not the entire line. So we get a line segment. And in fact, this tracks kind of strangely. If you were to plot some points on this, you would see that we can, depending on where we start, we can start here and head to this point in this direction, and when we get here, it sends us back to that point. So this is kind of a bidirectional set of points that we're trapped between these 2 points, 0, 1, 1, 0, and 0, 1, and we can never get any other points. So you could set up a table of values here. And depending on where you start, you'll see that you do nothing but track this set of points back and forth and back and forth. So is it a line? That helps. This is helpful, but we can't just jump from that point to our final graph. You have to pay attention to the original parametric equations and see how that governs. Do we have the whole line or do we have part of the line? So you could generate some points, and you would see that you'll do nothing but continue to get a set of points on this segment. So it's kind of hard to label the arrow going from one point to the other, one direction, and then from that point back to the first in the other. So you might just want to take it off of the line segment and show it like this. So there's an example similar to that in your book. So those are three pretty good examples of parametric equations. Here are some others, and you're probably not going to have to come up with these on your own. Let me put this up here since I prepared it. Should have put this up here a while ago. Would have been better than my picture, right? A whole lot better than my picture. So these are the first one that we looked at, the one that was actually in the book that had sine and cosine in it. And that was the unit circle. And you could see when t is 0, right? Much better than my picture. Now here's where your graphing calculator, I'll go through this kind of quickly, but since I'm not requiring a graphing calculator in here, this is in your book. Here's an advantage of using parametric equations when the picture is not a function. Well, a circle clearly is not a function, right? And you can use parametric equations in your graphing calculator, and you can actually graph the circle. Here's how you can graph something like this, which is not a function. Now you could split it up because there's really 4 functions here. This piece, this piece, this piece, and this piece. But that's a hassle. So you can accomplish graphing something that's not a function by putting the original equation, which is right here, in parametric form. And that's not that hard to do, especially in this one. And then you can actually, depending on the graphing calculator you have, you can watch it track that set of points, almost as if it had an arrow on it. So you can graph non-functions on your calculator if you put them in as parametric equations. See how to take the original? X is t, just put a t in here, and then just over here say y is t. So it's simple to break it down into 2 parametric equations. It's a way to get by on your calculator graphing in something that's not a function, and it'll do that for you. Okay, here's another one. Here's the function that we want to graph. Is it 1-to-1, and can we graph both the function and the inverse? Well, let's graph the original as a parametric set of parametric equations, and then graph the inverse as a set of parametric equations. You see the relationship there between the original and the inverse as far as the parametric equations? X equals t, y equals t, y equals this, x equals this, right? Flip-flop the roles of x and y, which we've already seen that. And then the picture, of course, you would also maybe want to tell it to graph y equals x, and you could come up with a picture like this. So you can graph all that simultaneously on the same screen. And you can see that the original function is 1-to-1, and so is its inverse. And then when they really get crazy, we'll finish up with these two. Clearly not functions, and you don't want to break this up into pieces to graph the function pieces. X equals t plus 2 sine 2t, and a similar definition for y. There's what it looks like. And your calculator will graph that for you, but it would not graph it if we tried to enter it in terms of x and y in the same function. So there's one thing your calculator can do with parametric equations, and here's another one. Wouldn't that be a joy to grab, right? So just plug in the parametric equations in your calculator, let it do the hard work. So if you've never used your calculator for graphing of parametric equations, you might want to check your manual to see how you have to enter them in, because it changes probably from one to the other. But it is an advantage, especially when you're dealing with a non-function, to enter them in as parametric equations. Okay, let me clarify. I'm not going to give you any new problems yet because we're not done. I think maybe the most important thing, and I knew we probably wouldn't get to this today, is the cycloid. Anybody dealt with a cycloid before? Okay, so we'll kind of start fresh with the cycloid. Let me make sure the problems from 1-6 that you have, because I think I mentioned yesterday that I was going to collect these, which I am. So the problem set from 1.6 starts on page 73. You may have these from yesterday. I want to make sure I give you the whole list. 17, 18. I guess I gave you 18 because somebody asked a question about it. Did I stop there?
No.
Does this look like the same set? 38, 51, 57. Okay, but that's due tomorrow. That's due tomorrow. And I will see you tomorrow.